Hey, hey, hey. Today we're going to talk about properties of integrals. And today might feel a little bit different from some of the other discussions that we have because usually I try and focus on one or two kind of big picture things. Maybe each of those big picture things has a few different examples, but it's kind of one or two things that we try and focus on. But today we are going to look at a whole bunch of definitions and theorems and properties all surrounding the definite integral. And all of these things, maybe aside from the definition is a big thing. We've been working up to this definition for a while. But the properties that we're going to look at are all little kind of self-contained things that we will end up using as we move forward in different ways. And they're things that we won't necessarily think too hard about when we use them later, but it is important for us to kind of set up the rules of what we're allowed to do with integrals and what we might expect with integrals. So that's what we're doing today. It's a little bit of a marathon of little steps that we're going to look at one at a time. And we're going to start with the biggest one, which is the definition of a definite integral, which, again, we've built up towards, and I just want to take a moment to look at it thoroughly so that we all understand where we've arrived at this point. So, if f is a function defined for x between a and b, we divide the interval from a to b into n subintervals of equal width, and that width is given by delta x equals b minus a over n. And the reason it's that is because b minus a is the width of the whole interval, and we're dividing it into n subintervals. We then let x sub 0, which is equal to a, and then x sub 1, x sub 2, all the way up to x sub n, which is equal to b, be the endpoints of those subintervals. And we let x sub 1 star, x sub 2 star, all the way up to x sub n star be any sample points in each of these intervals, so that x sub I star lies in the ith subinterval, which goes from x sub I minus 1 to x sub I. Remember that the first subinterval ends with x sub 1, the second ends with x sub 2, and the ith ends with x sub I. I know this I minus 1 might be a little confusing for some people, but just roll with it. We are looking at the ith subinterval that ends at x sub I. So we've got these sample points, and remember that we could pick any sample point in each of the subintervals, and it's the same. So then, the definite integral of f from a to b, that is the thing we're defining, is written like this, the integral from a to b of f of x dx, and it's equal to the limit as n approaches infinity of the sum as I ranges from 1 to n of f of x sub I star delta x. That is how we defined it earlier. It was a limit of Riemann sums, provided that this limit exists and gives the same value for all possible choices of sample points. If it does exist, we say that f is integrable on the interval from a to b, meaning we can integrate it on that interval. Now, I think the only bit that's really new here is this last bit, provided that this limit exists and gives the same value for all possible choices of sample points. There are some very weird functions that might not give the same value for all possible choices of sample points. Those are things that we will not look at in this class. Those are things that you would look at in more advanced math classes. And there are also different types of integrals. If you look into graduate level math courses and measure theory and all sorts of crazy weird stuff that's far beyond anything we're going to talk about today. But for now, we're not going to worry about any of the weird stuff. The functions we're going to look at, wherever they are integrable, we're not going to have any sort of weird issues about the limit not giving the same value. It's all going to work out fine. But mathematicians are like lawyers. They need to dot the I's and cross the T's. And so you will see long, wordy definitions like this where they're trying to make sure all of the loopholes are closed because somewhere in the world there are weird functions that cause those sorts of loopholes. All right, I will get off my soapbox and let's look at what sorts of functions we can integrate. And there is a nice theorem that gives us a very good family of functions that we can integrate. if f is continuous on the closed interval from a to b, or if f has only a finite number of jump discontinuities, then f is integrable on that interval from a to b. That is, the definite integral from a to b of f of x dx exists. So this tells us if we have a function that's continuous on an interval, we can definitely integrate it. That integral exists, it is integrable, we are good to go. But that's not the only type of function that we can integrate. We also know that if our function has a finite number of jump discontinuities on that interval, then we can also integrate it. Let me show you an example, a quick graph of what that might look like. All right, so here is a function that has a finite number of jump discontinuities. In fact, there are 2 jump discontinuities there. And when we have those discontinuities, we can basically chop up our area into different bits. If we draw kind of vertical line segments at those jump discontinuities, we are cutting this region into kind of 3 subregions. We've got a first one here that I'm going to very crudely shade in. And then we've got a second one that I will shade in here. I probably could just pause the video and do this, but I find it a little cathartic. Hopefully you enjoy it as well. Sometimes it's the little things in life. But so basically, if there's a finite number of jump discontinuities, we can separate our region into a finite number of subregions. We could call them R1, R2, and R3 in this case. And basically what we could do, instead of calculating the whole integral from a to b, we could separate it up into 3 smaller integrals here. So long as it's a finite number of jump discontinuities, it's a finite number of intervals, and they all have a specified width, and we can go through and just do the integrals on each of those, each of those subregions. So that is an explanation for why that is the case, why it makes sense that we should be able to integrate that with a finite number of jump discontinuities. That's not a proof for why we can do that, because remember, a proof would revolve around this definition with the limit of Riemann sums, and we'd have to look at Riemann sums with all of these different regions, and it gets a lot messier. So none of this is a proof, but just a very short explanation of why it should make sense that we're able to integrate a function over an interval where there are a finite number of jump discontinuities. I want to show you just 2 more quick things about integrals here before we switch to another video with more properties. All right, so here's another property up here, and we've got 2 integrals here, and one has a negative sign in front of it. Take a look at these integrals and see if you can spot what's different about them. You probably have already spotted it. The difference is with the limits of integration. We've got a up top and b down bottom here, and on the other side it's b up top and a on the bottom. And basically this says that if you have limits of integration, a lower limit a and an upper limit b, and you decide to switch those limits, you switch the upper and lower limit, then that new integral you get is the opposite of the original integral. So basically, if you're switching the upper and lower limits, you're kind of, in a sense, changing the way you're looking, right? We've looked at integrals from a to b, and we usually had a on the left side and b on the right side, so we were kind of integrating heading to the right. If you were to switch those and go from right to left, that ends up giving you the opposite of the integral that you had already done. Basically, if you're going in the opposite direction, you're going to end up getting an opposite integral. I don't want to say you'll get a negative integral, because it's possible that the original integral was negative. Maybe the function was below the x-axis. And then when you go in the other direction, the opposite of a negative is positive. So I don't want to say that, but whenever we are switching the limits of integration, the upper and lower limits, we end up taking the opposite of the original integral. All right, one more property in this video. And this is another one that's not terribly complicated. Here we have an integral of f of x dx, and the integral is equal to 0. And I want you to think about why this integral is equal to 0. If you look at the limits of integration, we're integrating from a to a. Basically, if you were to look at a graph, we would be integrating over an interval that has no width. And so if there is no width, it doesn't matter what our function is, there's going to be no area under that, and so the integral's automatically equal to 0. So truly, for any function, if you're integrating and the lower and upper limits are equal to each other, the integral is automatically equal to 0.